Conditional probability. Yesterday we talked about the Titanic, and we're going to continue talking about the Titanic for just a moment. Using the previously mentioned contingency table above, we can determine the probability that a randomly selected passenger survived given that the passenger was in second class. Let A and B be events, with A being a passenger in second class and B being a passenger survived. We want the probability of B given A. Such a probability is called a conditional probability. Yeah, so there's some different things you can do. Okay, so here's the definition right here of the event B given the event A. You see that little bar right there? That means given. Okay, so B given A is, and this is how you write it out, it'd be P, probability of A intersect B over the probability of A. Okay, so for the first example, we have an article in the Journal of the American Medical Association in 1997 reported that when people go to the doctor's office with a sore throat and think they might have strep throat, 30% actually have it. So that's something to know. It noted that the current test for strep throat was 80% accurate. And if you have strep throat, it's 90% accurate if you do not. Okay? What is the probability that a person who receives a positive result from the test does not have the disease?
Is it disease?
Yeah. So, in other words, what we're trying to find out is what is the probability of a positive result? Nope. And no disease. Because this is actually putting it into its formula, over the probability of a positive result. Now, the easiest way to do this is making up kind of a tree. So that's what I'm going to do. First, I'm going to look at B.
Why did you, I don't understand this.
Well, we haven't even got into it yet, Tori. Just give me a second. Okay, so B, we want to know,
What are you trying to find?
we want to find out what the probability of a person who gets a positive test but doesn't actually have strep. Okay? So, first of all, I'm going to divide my first group of people up to having strep, has strep throat, and has not. Nope, that's an intersect. Okay? So, we already see that 30% of the people that go in actually have strep. So I'm going to put that in decimal form, 0.3.
I was working in the dark.
Okay? So if 0.3 have strep, how many do not have strep? 0.7. Good. Okay? Next, I'm going to break this up. Because all these people are getting the test, right? So, positive test, a negative test. Do the same thing for the bottom. Positive test, and then a negative test. So it says already that it is noted that for a current test for strep throat is 80% accurate if you have strep. So, what is it? 0.8 here. And what would it be here? 0.2. Okay? Nope, just for this.
Oh, and 0.9 and 0.1.
Yeah, so the bottom, it says it's 90% accurate if you don't. So the bottom one down here is going to be 0.9, and this one's going to be 0.1.
Does the positive test mean that you have it or that it was correct?
So this positive result here with no disease was 0.7. The positive result here is 0.24 and 0.07 combined, because those are both positive results. You add them up, you get 0.31. You do the division here, you get 23%. And the results of that means that the probability of a person that receives a positive result and actually does not have the disease is 23% chance.
Wait, okay, why are you about 0.8?
I didn't mean to. So I can erase the 0.8 highlight here. Okay? All right, so let's go on. Next page. And basically all of these you're going to set up the same way. You're going to set up the little tree. Number 1B says, let B be a person that eats breakfast, and let L be a person that eats a good lunch. Suppose in a group of 80 people, 43 eat good breakfasts and good lunches, 21 eat a good breakfast but not a good lunch, and 12 eat a good lunch but not a good breakfast. And the rest eat neither. Okay? So, let's set up, first of all, our little tree. I'm going to do it over here. So, this is a good breakfast, GB, and a bad breakfast, BB. Okay? So, how many people eat a good breakfast? 43 out of how many total?
80.
Okay, 43 out of 80.
Should be 5.
Yeah, find the probability for that. If you happen to have a calculator, go ahead and find that. Bad breakfast. If it's 43 out of 80 have a good breakfast, how many have a bad breakfast? Yeah, 27? Is that what we said? 37. Okay?
There's 43 good breakfasts and good lunches, 21 a good breakfast, but not good lunch.
Okay, I did something wrong. Okay, so hold on. Trying this again. All right, so it said 43 eat good breakfasts and good lunches. So we're going to go down this road and then down this road here. So it's going to be 43 out of 80 right here. Okay? And then it says 21 eat a good breakfast but not a good lunch. So this would be 21 out of 80 right here. And it says 12 eat a good lunch but not a good breakfast. So that would be 12 out of 80 right here. And then the rest, if you were to add all this up, what would be left over would be right here. Okay? So if you were actually to put that in your calculator, this should be a 0.54. This one would be a 0.26. This is a 0.15. And this is a 0.05. So it says find the probability you have a good breakfast and a good lunch. What is that?
0.26.
Nope. 0.54. Good breakfast, good lunch. Okay? Now, this one says find lunch given breakfast. So, basically, that's the same thing as saying probability of B intersect L over probability of B. Okay? So, good breakfast given and good lunch, we already said was 0.54, so that should go on the top.
How do you know it's good?
Because I'm just assuming positive.
Wait, what probability of L given B?
Yep.
So good lunch?
Yep, good lunch, given good breakfast. Okay, so this is 0.54 on the top. Then it says on the bottom, what's the probability of having good breakfasts? I'm going to add these two together, right? So, look, anything that says good breakfast and good lunch is going to be this one and this one I'm going to add together. So 0.54 on the bottom plus 0.15. If you put all that in your calculator, you'll get a 0.675. Yeah.
Very good.
Why would you do like breakfast on the bottom?
Oh, you guys, I'm having really bad.
I'm writing in pen and you're just messing up my notes.
I would probably need a bucket.
Okay, but I was just color code, so I know what I'm looking at.
Color it and do it.
It's this one right here. Okay, you're right. I'm just having a bad day.
So you split them?
Yep.
Sorry.
Okay?
Yes. Okay.
It's actually that way in my notes, but I wrote it wrong on the screen. Having one of those days. Okay, so it's 0.65. 0.675. Okay, down on the bottom, this one is going to be the probability of B and intersect L over the probability of L.
Not just the last one.
Nope, it's a little backwards. See, this one's L given B, this is B given L.
But no, but on the other one, when you wrote it out, you said B given
Yeah, the top part stays the same, but this one, notice that they're reversed right here. So I'm going to divide.
L.
Yeah.
Oh,
Okay, so this is going to be 0.54 on the top again, divided by 0.54
and
and 0.15. Okay, so then that should be 0.782, and I checked my work, that's right. Thanks for bearing with me. Whew. Example 2A. Suppose that all the patients are tested for a serious disease that is estimated to be found in 0.5% of people. Suppose also that the test accurately spots disease in 98% of the time and accurately indicates no disease 95% of the time. What is the probability that a negative result is a false negative? All right. So here we are. We're going to make this little tree thing again. Has disease. Okay. Doesn't have disease. Okay. So already we know that only 0.05 of the people have this disease. So I'm going to put 0.005 in, because that's 0.5% in decimal form. So if only 0.005 of the population have the disease, how many don't have it? Good, 0.995. Okay, so now let's break this up over here. We're going to have a positive test and a negative test. So I'm going to just put plus, minus. Plus, minus. Those of you that need to go, you can go. Okay, so positive test. It says, suppose that the test accurately spots the disease 98% of the time. So this would be 0.98 right here. Yep, 0.02 right here. Okay, and then it says it accurately indicates no disease 95% of the time. So this would be 0.95 right here and 0.05 right here. Okay? So what we're actually looking for in this one is a negative result intersect has disease over a negative result. Okay? So negative result intersect has disease. What is that going to be?
0.005 times 0.02.
Yep. So I'm going to multiply these two together, and that ends up being 0.0001. So it'll be 0.0001 there. Okay, and what are my negative results? I need to find this one right here. So 0.995 times 0.95, what is that going to be? If you multiply it out, you get this, okay? So on the bottom, I need to add these two together. 0.945 plus 0.0001. If you were to multiply all that out, you actually end up with just this. It's so small, it doesn't really change it. Okay?
Wait, so what do you multiply 0.955
By 0.995. So you're actually going to multiply this times this to get this. Okay?
Wait, and then how did you get the
This one, I got that by this times this equals this.
Carrie, I'm not looking at it.
Okay?
Are you
All right. So on this last problem, we're supposed to suppose that one in 500 airline passengers carry some hazardous material on them when they are on a plane. Further, suppose that an airport screening device accurately identifies 98% of the people with hazardous material that pass through it, and accurately identifies 99% of the people without hazardous materials. If a person is identified by the machine as having a hazardous material, what is the probability that the person actually has these materials? So let's make our tree.
We don't know
Even in 1 out of 500.
Yeah, we're talking about 1 in 500. Okay? So has the hazardous material. That's 1 out of 500. And if I were to divide that, it's 0.002. Okay? Has not.
Oh, yeah, that's just.
0.998. Good. Okay, so now we're going to have a positive screening and a negative screening for both of these. Because it's 1 minus this. Okay? So positive screen, negative screen. Dang it. Positive screen, negative screen. Okay? So, here we got this 1 out of 500 right here. And this number right here is 1 minus 0.0002. That's how you got that one. Okay? So, positive screen, they said 98% of the time we get a positive screening. So that's going to go right here. So that being said, what's going to be a negative screening in that one? 0.02. Okay? Now going to the negative end, it says it identifies the negatives 99% of the time. So that will be right here. What would the positive screen there be? 0.01. Okay? So if you follow along and you multiply each of these out, so 0.002 times 0.98, that would be a 0.0196 for a point right there. This one would be 0.0004 multiplied through. This one would be 0.0998 with a point. And this one would be 988. Okay. So I'm just multiplying down my road as I go. So 0.002 times 0.98 equals that, and so on. Okay, so what we're actually looking for now is the probability of a positive screen intersecting with actually having the material over the probability of a positive screen. Yeah. So, positive screen and actually have, that's 0.00196. Okay, and then look at our positive screens. We need to add those together and put it right here. So we have 0.00196 plus 0.00998. Yep. Okay, and when you do that, 16.4% chance. Okay?
Wait, it only about 16.4% of the people that actually have hazardous materials?
If a person is identified by the machine as having a hazardous material, what is the probability that the person actually has them? So if, yeah. So in other words, it's going to pick up way more people having the hazardous materials than the people that actually have them. Okay?